This is the last day of x64 programming, and we're gonna try to knock off a couple more problems before the month is over. Let's start by picking a problem. So I think we just start. We skipped a few here, and quite frankly, I skipped them because I'm not that interested in doing any of them. This might be a fine one to do. I think I skipped this one. I'm not signed in anymore. That hasn't happened on one of these streams yet. Let me just pop this over here and sign in real quick. Okay. So as I was saying, we could look at this one. I think this one was a fine problem. I just skipped it because it was too complicated at the moment that I hit it. So let's read this one real quick and see if we want to do it. Let the function d of n be defined as the sum of proper divisors of n, numbers less than n which divide evenly into n. If d of a equals b and d of b equals a, where a does not equal b, then a and b are an amicable pair, and each of a and b are called amicable numbers. For example, the proper divisors of 220 are 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. Therefore, d of 220 is 284. The proper divisors of 284 are 1, 2, 4, 71, and 142. So d of 284 equals 222. And that makes, they didn't say this, but I'll throw it in there, that makes 220 and 284 an amicable pair, and they're both amicable numbers. Then it asks, evaluate the sum of all of the amicable numbers under 10,000. Okay. So I think we should do this one. It's kind of an interesting one. Let me think about how would we go about, what we need to think about is how we would go about evaluating the d function. Because if we could evaluate the d function for every number between 1 and 10,000 quickly, then we could just build a little table, and that table would then be what we need to check for amicable pairs, right? To find out if something was a pair, we would just look at the number at that, look at the slot, you'd look at the number on the table, see what its evaluation at d is, and then if that number, when you look it up in the table, goes back to the first slot, so they form a cycle of 2, then you found a pair. If it goes outside of the table, then you just evaluate that number in place and check it there. In fact, if we can do it quickly, we might not even need to do the full table thing. The table thing would really only save us re-evaluations. Well, it would save us about, you cut the number of evaluations in roughly about half, maybe. A little less than that, but something like that. Anyway, let's focus on the more important part, which is how are we going to evaluate this function d of n. So let's see, this is problem number 21? All right. All right, problem number 21. Let's write this in like very mathematical notation because that's the way I like to read things. So we're going to say, let's say that f is ranging over the divisors. I'm going to write that with a capital D because it's a set. Divisors of n. And f is not equal to n. We're adding that up. So how about I call that the divisor sum function? We want to figure out a good way to evaluate that. So I don't think it's going to be super easy, but I'm going to start with maybe something that's a little bit of an oversimplification. So I'm just going to write down some values of this and see if I can suss out any good patterns. It might turn out that the only thing we can do is generate this set and then sum over it. And if that's the best thing I can think of, we'll go down that road. But I want to see if I can come up with any better plans than that. Because if that is the best plan, that kind of sucks. There might be so there's two different paths I could think about here. One is there a better closed form version of this function at all? And that better closed form doesn't have to be totally closed form, just something that is easier than generating the set of divisors. And if I can't do that, then maybe I can generate this in a batch. Because I was talking about doing it as a table. If I can, for instance, evaluate this function in 1,000 locations or 10,000 locations, using about as much work as it would take to evaluate it in one location, then that would be a good start too. So actually, let's start with my first idea. I'm going to write down values of n versus values of d of n in a table here. So 1, 1, 2. So the divisors of 2 are 1 and 2, so that has a sum of 3. 3, 1 plus 3 is 4. With 4, we get 1 plus 2 plus 4, so that's 7. With 5, we get 1 and 5, so that's 6. With 6, we get... Oh, you know what? I'm doing this wrong because I'm supposed to... Okay. Let's back that all up. I'm just going to do undo here and we'll reset. Okay. So 1 is just going to have 0 because we don't count the case where f equals n. 2 has 1 and 2, but we don't count 2, so just 1. 3 has just 1. 4 has 1 and 2, so that's 3. 5 has 1 and 5. We don't count 5, so 1. 6 has 1, 2, and 3, so that's 6. 7 has 1. 8 has 1, 2, and 4, so that's 7. 9 has 1 and 3, so that's 4. 10 has 1, 2, and 5, so that's 8. 11 gets a 1, 12, 1, 2, 3, 4. Wow, 1, 2, 3, 4, and 6 all work. So 1, 2, 3, 4 adds up to, let's see, 1, 3, 6, 10, and 6, so 16. 13 is a 1, 14. 1, 2, 7. That gives us 10. I'll put in one more. 15 is 1, 3, and 5. So that's 9. Okay. So a couple things jumping out at me. Primes are obviously going to get they're always going to be a 1. So what's going on with powers of 2 is kind of interesting. Like if I did 16, I think you could see it even more clearly. So does 16 have 1, 2, 4, and 8? So that's going to be 15. So the powers of 2 are n minus 1. So what happens with powers of 3? So that each... let me look at a couple more powers of 3 real quick. So powers of 3 include 1, 3, 9, 27, and let's throw in... what is that? 81 is the next one. Right, so that gives you a 0 here, a 1 here, a 4 here, and you add in 9, so you get 13, and then you add in 27, so you get 40. So these are all n minus 1 over 2. So it seems kind of like if you have some prime p to the power n, what are its divisors going to be? Suppose p is prime and n is some natural, then d of p to the n is going to be equal to 1 plus p squared plus plus p to the n minus 1. Or to write it in a more formally precise way, we have the sum as I goes from 0 to n minus 1 of p to the I. And it seems like we could use like a geometric series trick there. That's turning out to be n minus 1 over p minus 1 for some reason. No, a geometric series would be if we were multiplying these over and over again. But let me just think. Suppose let me think. Oops. Didn't clean it up. I think it's going to hold like this. Let's just look at powers of 5 real quick to make sure that the pattern is making sense. Okay, so 1, 5, 25, 1, 25 is going to look like 0, 1, 6, and then we add in 25, so 31. Now, can I subtract 1 from that and divide by 4 to get this? Yes, yes, yes. Okay, so this is powers of 5 are n minus 1 over 4. So I'm going to claim first of all, let's finish up this thought. P prime n natural implies that d of p to the n equals the sum y equals 0 to n minus 1 of pi, right? Claim that the sum of this is equal to n minus 1 over p minus 1. And we're assuming p is prime and all that still. So let me just write that a little bit more cleanly here. So claim p prime n unnatural gives us that d of p to the n equals n minus 1 over p minus 1. So let's see here. Let's suppose that p is prime and n is a natural. then we know, actually, let's do this like recursively. Let's suppose that k less than n implies that our claim for k is true. Then what we can say is d of p to the n well, let's do this. Let's first introduce p prime then d of p to the n is equal to d of p to the n is equal to the sum from I equals 0 to n minus 1 p to the I. But we can split that up into two parts. So we can say I equals 0 to n minus 1 minus 1 p to the I. So that's like minus 2, but I'm splitting it out like that for a particular reason. Plus p to the n minus 1. And then what I can do is say, okay, this right here fits the pattern of d to the p to the n minus 1. So we can rewrite this as d of p to the n minus 1 plus p n minus 1. Let's see, then if we look at that, that will, because of the claim, we can say, so the claim works, this is less than n, so we can apply our claim to it, and our claim is that that is equal to n minus 1 over p minus 1, so we can say that that is equal to n minus 1 minus 1 over p minus 1 plus p to the n minus 1. So let me combine that into an n minus 2 and a p minus 1, and let me turn this into p to the n minus 1 times p minus 1 over p minus 1. Then I can combine the numerators. N minus 2 plus p to the n minus 1 times p minus 1 all over p minus 1. I can combine these, n minus 2 plus p to the n minus p to the n minus 1 all over p minus 1. Doesn't quite look like what we wanted to find. We want this to say n minus 1 right here, but instead it says this, which is much different. Let me double check that I did everything right. So that is just how the sum works, this lazy way. I peel off the highest one and put it over here. So the n minus 1 case lives over here, and then the rest live here. That's the dpn minus 1, which means we can apply the rule, and we get n minus 1 minus 1. Like, that's the n minus 1 over p minus 1, right? I multiply this by the same thing on top and bottom. Yeah, there's no way that this is positive 1, right? The difference between those two things isn't going to be a positive 1, which is what we would need for it to make our formula add up. So it seems like either our formula is actually wrong or the proof has a mistake in it somewhere. But like this part's very solid. It n minus, so there's, wait, is this n minus 1? 4, yeah, so 0, n, wait, that's not n minus 1. Okay, this is wrong. This is, okay, that's part's right. That's n minus 1, but I wrote the rule down wrong over here. Okay, this is not n minus 1. This makes more sense. It's p to the n minus 1 over p minus 1. Okay, so if that's the claim, then all of this is wrong up to this point, because that's where we invoked the claim. So we got the claim details wrong the first time through, but now we can resume from here. So this part is all good. And then when we replace this with, by using the claim tells us actually that this is p to the n minus 1 over p minus 1 plus p to the n minus 1. Okay, now it looks like it might actually work. So then we want to write p to the n minus 1 over p minus 1 plus p to the n minus 1 times p minus 1 all over p minus 1. Combining those, p n minus 1 plus p n minus 1 times p minus 1 all over p minus 1. Okay. And then what's going to happen is we expand out that parenthesis. So we get p n minus 1 times p, so that becomes p to the n, minus p to the n minus 1 all over p minus 1. Okay, so now this and this cancel each other out, and all we have left is p to the n minus 1 over p minus 1. And that is cool, because that connects d to the p, d of p to the n, after all these transformations, to p to the n minus 1 over p minus 1, which means we have proven that the claim is true for the number n. Okay, so if I zoom out here, that means all of this tells us that if p is a prime, then we know that claim holds for n. And of course, that means we can write that all of this together means that if k is less than n, that implies that if p is a prime, that implies that the claim holds for n. So then I can rearrange this to get what I want, which is that when p is a prime and oh wait, sorry, I wrote that last part down wrong. It's going to get a little complicated here. What I showed there was that if k is less than n, technically our claim already includes p as a prime. it's a little confusing where I want to put that part. So here I showed that if P is a prime, I'm just going to back this up for a second because I think I didn't quite do the details right. It should all kind of fit together like a puzzle. So the thing we showed, I'm going to just summarize it in one step down here, is that d of p to the n is equal to p to the n minus 1 over p minus 1. So we have that if p is prime, we get that d of p to the n equals p to the n minus 1 over p minus 1. So that is the same thing as claim of n. So then we can say that when k is less than n implies claim of k, then we get claim at n. So that's the inductive step there. So by induction, I think that this is true. So whenever we have a power or prime power, this formula here should hold. So now I wonder about combining those. So let's look at 6 as an example. Does that help us at all with the case of 6? Six is 2 and 3. 1 plus 2 plus 3. 8 is 1 plus 2 plus 5. So 2 and 5 both have 1s there. So when this combines, it like doesn't really fit any obvious. Like 5 and 3 are just going to be primes there. So when I combine those, maybe that doesn't work. But let me think about 6, 10, 15. So who's the first thing with 3 factors? 2 times, so 12 might be interesting. 16. So 12 contains 1, 2, 3, 4, and 6. So it contains all of the divisors of 6, which covers 2 and 3. That gives us this, this, and this. Two. So is 6 like... We include the 2 itself, the 3 itself. But that double counts that and you get 7. 12. We include 6 plus everything that 6 has, so that gets us to 12. Plus 4. And that gives us this doesn't really seem good. I see that this definitely works as a quick way to compute this for anything that's a prime power, but it does not look to me like there's any obvious way to combine composite numbers that aren't prime powers out of, like, there's no way to build 6 out of the results of 2 and 3, for instance, or 12 out of like any of these things. So 12 could be seen as like factoring into 6 and 2, for instance, and that doesn't help you. Like, you know you need 6 and 6, but the other thing you need is 4 itself. You're missing like, you have to include this and this, plus all of the divisors that are underneath them, and if they share some divisors and not others, then you don't know how to combine those. So I don't think that's a particularly easy way to do it. So I'm thinking maybe, wait. So I think let's, so that doesn't look promising. So instead I have a different idea that I wanted to explore. So that was the first idea, was let's look at the closed form thing. It's feeling dead-endish to me. So I'm going to propose let's try to generate a batch instead. So changing tacks here, instead of saying let's make a function that just one off, you put in and you get out the divisor sum value, let's instead say, look, we need, for this particular problem, we need to check a bunch of divisor sums in a contiguous range. Maybe that's something we can do pretty easily. And the very first thought that occurs to me is that we could do this in a kind of sieve-like manner. So what I mean by that is we could go, like, let's draw the table that a sieve would use. So we want 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, I'll color out that part. We won't use that part. And then a couple of rows here. So if our table's like this, we have like, here's 0, 10, 20, 30, 40, and you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it wouldn't be a two-dimensional grid in memory, obviously, but just for fitting it on the screen, I'll lay it out that way. Let me make this 2 more of a 2. So what I could do is go like, okay, first I see a 1, and I need to add 1 to everything. So I would have like a 1 everywhere. I'll stop after 1 row for this part though. Then what I would do is I go, okay, next up is slot number 2, and I need to go 2. So you don't put it in that one. You go skip ahead by that much and then add 2, add 2, add 2, add 2. And of course, like down here, we would end up with this pattern just repeated. So I'll extend it to there. Then 3, we would skip ahead by 3 and add 3. See what I'm getting at though? It's like the same idea as the sieve. Oops, I need to add 3, not write 3. Except instead of overwriting squares, we're sort of increment or adding into squares each slot. So let's see, 12 gets 3 more. 15 gets 3 more. 18 gets 3 more. 21 would have a 1, and so it becomes like that. And we go, okay, 4. So 4 doesn't get modified, but 8 does. So that becomes 7. Adding 4 more to here becomes 10. Adding 4 more to here, it becomes 7. Adding 4 more to here, that was a 3 already, so that becomes 7, and so on. You do the same thing for each number, right? So for each number, then I would take my 5s and I'd go add 5 here, add 5 here, add 5 here. Now, is that fast? Is that faster? So if I do it that way, then what I'm saying is for every number in this table, I'm going to iterate across the table. So I'll have to fill it with 1s and then fill every other number with a +2 and every other number after that with +3, or every third number with +3. And so the amount of work I have to do is n, 1 for every slot in the table, squared, right, times however many iterations I have to do for all of them. So it's like an n squared iteration across the size of the table. And the alternative, like naive thing I could do, is literally just look at each number and go from 1 to n. So it's kind of n squared either way, right? Like if I took the number 21 and I looked at all the numbers from 1 to 20 and checked each one for whether it divides 20. So one thing is this avoids division. It does everything with simple adds instead of divides, which would be faster that way. But it's still n squared. And the difficulty is, like, I don't know, is there any way I could grow this? So maybe let's look at this as maybe, let's try a different approach. So a sieve maybe isn't going to work, or it would work, but it isn't necessarily the best thing we can do. Let's see if there's any like table growing version of this thing. So it would start off with, technically I should have put a 0 here too. A 0 here, and then I would grow it. So I'd go 2. Well, 2 has a divisor of 1, so I'll add 1 in. And then I look at 3, I add 1 in. How is this going to be better? So when I look at 4, I look up the factors of 4 and find out that 2 is a factor of 4. So I add in if I can take any number and split it into 2. So if it's a prime, I'll just put a 1 down, right? If I can split it into 2 numbers, right? If I can say 4 is 2 times 2, then what I can do is say, all right, then what I need is on the side that's a single prime, so 4 is 2 plus whatever is in the 2 slot, so that's 3. 5 is prime, so it gets a 1. 6, okay, so say I look at my factor table and I find a 2. So then I'll know, okay, I need to take however many factors there are of 3, which is 1, plus 2, so that's 3, but I also needed to add 3 in that case. How do I know when I need to add the extra 3? And you know, that won't always work, because if I divide out 2, like from 12, say I'm in the case of 12. I'll look at my factor table and say I find a 2 there. Then I would divide out the 2, and I would have a 2 on one hand and a 6 on the other hand. And if I were to say, okay, 6 has 6 slots, and I add in 2, obviously that's going to be wrong, because we've already noticed that this algorithm I was proposing didn't work. But furthermore, it's even trickier because I actually have already counted the 2 right here. So what I really need is, on one hand, all of the the fully saturated power of one prime factor, right? So if I have 12, I don't pull out 2, I pull out all of the 2. So I pull out 4, and then I have, on the other hand, whatever's left over. So if I split 12 into 4 and 3, and I add them all up, I don't get the right answer, right? That's 11. That's not right. 1 plus 2 plus 4. Yeah, I'm still missing the 6 in that case. And I've added in the divisor of 1 twice. Yeah, none of that really seems to be helpful. This is a tough one. I mean, I have a solution. It feels like there ought to be some way to make it better. So I think one thing that might help is if I were to okay, so let's just try and explore something. Not sure which direction we want to take, but let's explore something here. So let's just write out the numbers. Instead of doing it the way I have before, I'm going to divide it like this. Thank you, Windows, for your timely interruption. And back to the stream. I'm going to write out some numbers like this. And then I'm going to write out the divisors on the left side here. So 1 has no divisors. 2 has the divisor 1. 3 has the divisor 1. 4 has the divisor 1 and 2. 5 has the divisor 1. 6 has the divisor 1, 2, and 3. 7 has the divisor 1. 8 has the divisor 1, 2, and 4. 9 has the divisor 1 and 3. I'm going to keep going here. Ten has 1, 2, 5. 11 has 1. 12 has 1, 2, 3, 4, and 6. 13 has 1. 14 has 1, 2, 7. 15 has 1, 3, 5. 16 has 1, 2, 4, 8. 17 has 1. 18 has 1, 2, 3. Let's see, that's not going to have a 4 in it. 5, it's going to have a 6. It's going to have a 9. Right? No 4, so under 12. Got the 2, the 3, the 2 times 3, the 3 times 3. And then if we do the 2 times 3 times 3, we're back to 18, we're done. So let's stop there. Let's think about, instead of thinking about these in terms of sums, can looking at the sets make this any clearer, like give us any ideas of what we could be doing? So maybe this would be easier if I wasn't just doing proper divisors, but all of them. And the reason I say that is, if we look at the case of, let's look at the case of 12. This could be seen as like the table 1, 2, 4, 3, 6, 12, right? If I do that, then it's this nice orderly combination of things where I have 2 to the 0, 2 to the 1, 2 to the 2, 3 to the 0, 3 to the 1. And so I could then calculate this, right? And subtract 12 after the fact. Maybe that approach like that would be good, because then I think a lot of these tables become simpler. Let me just do a couple more of these to show how all of them just become this same regular thing. So this has a 1 power of 2 and 1 power of 5 in it, because we're looking at the 10 case here. So the table this creates is a 2 by 2 table that goes 1, 2, 5, 10. Now every number in that table is going to be unique. But what I could do is say this here is all we have to compute, right? That is known to us. That row is known to us. That is P. So that is, let me write it this way, 2 to the n minus 1, right? Is that how it worked? 1 plus 2 plus 4. So if I have a 4 here, then this is going to become 7. So that's 2 to the 3 minus 1 over 2 minus 1. And this is just using that same idea we had from earlier about powers of summing the powers of primes. So this here is going to be 3 squared minus 1 over 3 minus 1, right? Now, why is that important? Because then, all of a sudden, I can just multiply those two things, and I get the total of this whole table, right? Because this row and this row are the same thing, except the second one is times by 3. Or I could see it as this column gets repeated twice, and here it's multiplied by 2, here it's multiplied by 4. So this whole thing, the sum of all of this, could be viewed as 2 to the 0 plus 2 to the 1 plus 2 to the 2 times 3 to the 0 plus 3 to the 1, right? That's the sum of the whole thing. And that means I could rewrite that as these simpler closed form things for each prime power. 3 squared minus 1, 3 minus 1, right? So that's what we want to do. Here's our idea. Let's shift from summing proper divisors. Idea. Shift from summing proper divisors to all divisors. So if D is the sum of proper divisors, then let's compute D hat of n is going to equal the sum over all of the divisors of n. And remember earlier, we wrote down f not equal to n, right? This is the very beginning of the thing. We said f not equal to n when we wrote down D. But that's just making it harder to compute. It's actually way easier to compute this guy, because then we can rely on this table to be complete. There won't be a missing slot at the end of the table. And then D of n, our goal, is just D hat of n minus n, right? That's easy enough. So there we go. Sum of divisors looks like the solution to our problem. So then all we have to do to make a sum of divisors okay. So our idea then is when n equals p to the k for some prime p, then we know that d hat of n is just 1 plus the prime plus the so we already did this. It's like p to the k plus 1. Earlier we were excluding the last p to the k, so it's all shifted by 1 now. Minus 1 all over p minus 1. And then when n is equal to p sub 1 k sub 1 times dot 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 p sub r k sub r for p sub I primes, then I'll actually write p sub I are distinct primes, then d hat of n is just equal to the product when let's have I equal 1 to r of d hat p sub r k sub r. So we do this case, the prime power case this way, and when we need to combine multiple primes, so we don't have a simple prime raised to a particular power, but we have multiple primes combined, we just combine them, we do them each separately, and then combine them using this rule. I think we can do that. I think that's within the realm of possibilities. So, now we need to figure out how we're going to decompose a number into its prime factorization, because that's the main thing we're going to need. Now, is this something we've done before? I think we've relied on a prime factorization before, but I don't think it was quite as hard. So I think when we counted divisors, we had a similar situation come up. Big nums, products, combinatorial, colats, Pythagorean, long division. Oh man, this was a while back. Parser. Okay, so yeah, this is the problem right here. Problem number 12, we were counting divisors instead of summing them. And we had to count the divisors. So what we did was we used max div, right? So max div told us we pulled out one factor, and that was always a prime factor, f. And we then did a max divide operation to find out how many times does this prime factor occur. So that gives us our power. If we find the max r that has this property. Then we combine them into an accumulator by the multiply. So it's going to be the same thing, except instead of combining by n plus or r plus 1, we have to combine by a different thing. That's all it has to be. Okay, that's cool. So we're gonna pull out one prime at a time and fully pull it out using our max divide trick from before. So our new algorithm, let's write down the algorithm now for the whole thing. Algorithm. Okay. So the algorithm for d hat of n is going to be, first we grab f from a factor table. The factor table always gives us a prime factor, right? That's its job. And then we do max divide. So we get, I'm going to say a pair here, n prime and r. This is equal to the max divide n divided by f. So that'll tell us how many times we can divide n by f. And give us the new number that you have when you've removed all of those. Then what we want to do is we want to accumulate so we have this product here. What are we accumulating? We're accumulating the simple version p to the k plus 1 minus p over p minus 1. So we want to accumulate p to the r plus 1 minus 1 over p minus 1. And I guess I kind of wrote this down wrong. I didn't include the stuff before. That's all inside of a loop. So let me give myself a little more space here. D hat of n looks like set an accumulator equal to 1, loop, and then right in here, I need to inject, if we put that in, and it turns out our n is, or actually what we want to do is, so what we want to do here is if our n prime is equal to 0, then we can break out of the loop. Otherwise, we update n with the value of n prime. And we keep looping. And then we also need a case that's like, hey, up here at the beginning, if n equals 1, just return 0 immediately. Don't play the game. And then down here, we return the accumulator. Okay, there's our algorithm. That shouldn't be too bad. The hardest part is going to be optimizing this guy. So right now, when we do the max divide thing, we are counting the number of repetitions and the final n prime comes out. But we could also actually compute p to the r at the same time, right? Or I guess not p, I should have said, let me just change the name of this to p. So p comes out there, p goes in there. We could also compute p to the r while we're at it, because that would be easier than getting just the power part and then having to use p to the r or compute p to the r separately again, right? So we'll make a max divide alternative that does 3 things out instead of 2 things out. That'll be the plan. Alrighty. 8th Mage, yeah, if you've got a suggestion, what do you think? You can add powers. I see, you're right. Okay, so instead of this, Right. Let's expand all of this in line. And the reason I say that is because then we can avoid having to write a different helper function and a separate function call here. We already have to use a function call for this part anyways, but here we can, instead of doing a function call, we'll just have an inner loop that does this work. So it'll do iterating the divide, and instead of computing the power r, it will just sum them up. I think that, I don't know how reusable that function really is. I mean, mathematically it's a useful idea, but it comes, you know, you end up wanting different things from it, and I don't want to have like 10 different versions sitting around that all have ambiguous and confusing names. So since I don't really have a good way in assembly to write down, in fact, we didn't have this in C or pretty much any programming language, it would be kind of hard to abstract the idea of the max divide thing in the way that like allows it to return all sorts of different types depending on the use case, and then like optimize the details, right? So anyway, let's just let's do that. That's a good suggestion. In case that wasn't clear, I'll explain what 8th Mage's suggestion was. So this here is the closed form way of computing the sum of the primes. Remember? So like up here, when we were doing this thing, it was like, if I wanted the sum of 125, I was doing, this is actually the sum of everything but 125, but it's like, if I do the sum here, 1 plus 5 plus 25 plus 125, I just realized I made a mistake earlier too. 1 plus 5 plus 25. Yeah, a callback wouldn't make sense. That's going to be even, I mean, you might successfully abstract it, but it's going to be a worse pessimization than even having separate like function calls. I mean, it'd be worse than having a divide at that point. I could have just done n divided by n prime, for instance, and it would have been faster. Anyway, 1, 5, 25, 125. So the idea here is, as you're adding these up, we found this formula that we ended up on, which was like p to the k minus 1 over p minus 1, right? So here we have n represents the 5, 25, 125. So that's our p to the k, and the 4 is the 5 minus 1. But this closed form thing, it turns out, is going to be harder to get than just, we're going to have to do this loop anyway. So we're going to just accumulate the sum there, because when we do max divide, like the best thing we know how to do at this step is a loop anyways. So it's actually not an optimization to use the closed form equation in this case. Anyway, let's get a little groove going on here. Let's go write some code. I never did this. I'm gonna just get rid of this stuff. I was kind of thinking about saving it, but I say no. Alright, so here we did divisor count. Let's put in divisor sum. It's going to take the fact table, the count, and the n. Let me know if the music is drowning me out or if it's annoyingly too quiet or something. Okay. So I did make one other mistake here, which is I said if n equals 1, return 0, but we don't actually need that. Because this is not the version where we exclude or we're doing proper divisors only. So instead, we'll just take this and transport it up to the beginning of the main loop. Okay. Now we need to be able to make function calls here, so let's plan for that. Which the get prime factor is the function call we want to be able to make. So, what was it? We needed to subtract 32 from RSP whenever that happens. And when we're done, we'll do that. Then we were doing alloc stack 32 and prolog here. Okay. So now we're set up with a function callable space. Let's set up our accumulator equals 1. We need to put this into a register that can, let's see, yeah, it's got to persist. I don't think, the only two things that need to persist are n and the accumulator. So I think we can get away with 2 non-volatile registers. Cool. So we're going to set RSI to 1. Move n. Actually, I need the factorization table and the count to stay around 2. That's fine. For those, I will... How do I want to do this? Okay, so I could just use the shadow stack space. I could also just use that for n, of course, which is kind of interesting. Let's try that path today. I haven't tried that a lot. Let's see how that stuff looks when I do it that way. Don't necessarily need the new song on loop all day. We can switch to this playlist. All right. So accumulator goes in RSI. I want to push into the first 32 and 40 more, or 8 more. Let's see, 40, 56, there we go, okay. RDX, R8. Okay, so I've set up an accumulator. I've set up my parameters so I won't lose them. Then the loop begins. The first thing we want to do is test n. So if n equals 1, we'll say this is less than or equal to 1. Go to done. There, we're going to move into RAX, the accumulation. Okay, and then if n is less than or equal to 1, we go to done. So compare R8, which contains our n with 1. Jump if that is below or equal to done. Okay. We're also going to have a jump back to loop 0 here. So there's our loop body. Now we want to call get prime factor. So we're going to move into RCX. We're going to just like undo this thing. And that might be unnecessary, but just for a starter pass, I'm going to do that. I think we might already be able to guarantee that those are there, whether we're flowing from up above or stuff below. But we'll just fill in the parameters that we've got and call get prime factor. Now RAX contains our prime factor, and we want to call max divide, or we don't want to call max divide, we want to do like a loop 1 kind of deal, right? So loop 1, and R8. We can't assume that's not been modified, so we'll need that again. Yeah, okay. So the way max divide works is it's going to be a loop that repeatedly divides, does n divided by p. So we're going to be doing our numerator So let's see, which register is going to hold P? Let's put it into RCX. Let's 0 RDX out. Now we should be able to do, I want that to be U64. We should be able to do, and also I'm not even, this should be an R8D, EDX. Try to keep this consistent now that we got it all right last time. P gets moved to RCX, we zero out RDX. Okay, now we're going to do the divide. So we move into RAX, the numerator. So the numerator is N, which is living in R8. N, which is living in D-word putter. RSP plus 56. Okay. And then P is in RCX. Do an 8-byte divide there intentionally. Now Q is in RAX, R is in RDX. If R does not equal 0, go to, we're going to call this done 0. And now we're going to go to done 1. So that's the done for this loop. All right, so test that register. I guess I should test this register, right? And then jump if that is 0. Jump if that is not 0 to done 1. Okay, R is not 0. Okay, if this is divide by, or if this division is not full, so when this has remainder, it means we didn't have a clean divide, so we jump out and we're done with this part. Now what we need this time, we don't actually need R. What we need is this, which we can compute by summing the powers of primes together, right? So we're going to have n prime. Okay. So every time we divide, we get a new value for n and a remainder. If that remainder is not 0, we're done. Otherwise, we'll keep looping. And then what we want to do is we need a couple of accumulation things set up. So P power equals 1. So we'll put that in R8. And P sum will be 0. Put that in R9. And then the idea is at each step, if I didn't jump out, then I had a clean divide and I want to do P sum plus equals P power. So that's add into R9 from R8. I think you want to do something like that, right? And then P power times equals P. So we want to do technically I could just multiply P in place, and instead of, yeah, I'd actually have to, I feel like this is actually better because now I don't have to modify N each time. I can use the in place modified N. So yeah, we'll keep doing it this way. So I multiply by P, which is in RCX. And so when we're done, RAX contains the N prime, which we want to assign back into N. And R9 contains our accumulated value here, the one we did without doing it in closed form. So we just added up all these prime powers, and now we're going to multiply that into our main accumulator. So our main accumulator, is RSI. So when done one happens, we go move back out to the slot for N. From RAX, or I suppose from EAX. So here I'm doing an 8-byte divide, but here I set it from a 4-byte. It might be better when I did this. I read 4 bytes there. I'm counting on it to clear that to 0. Do you get partial register stalls when you store 32 bits, but then use 64 bits? That's a question. Do you get partial register stalls when you store 32 bits, but use 64 bits? Jesus Christ. All right, what is all this? Can I get No, I'm not going to find it this way. I'll ask later. We'll ask later. So it's unclear to me whether or not switching from, because this is going to become a 64-bit input to this, but it knows, unlike other cases, it knows the top bit should be cleared to 0. So setting this is kind of similar to setting RAX. But if I actually set RAX here, I could get a bug, because I haven't actually set all 8 of these bytes. I've set those 4. So I'm reading 4 bytes into this register, and I'm saying, I hope you know that since you're always going to clear to 0 the high bits, that when I switch to 64 bits, you don't have to do anything fancy to figure out the whole value. Yeah, I wasn't really trying to go to Stack Overflow. It's just that's what comes up when you search on the internet at all. I feel like the only way to actually answer to these things is to talk to a person, because like searching the internet in general just doesn't tend to work very much. Okay. Go to done one. R8 P power times 8. Boom, 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 boom. Okay. That's good. Move n back to the stack memory. We'll maybe reconsider that idea in a little bit. But then the other thing we wanted was accumulate, right? So our accumulator times equals our p sum. So we want to imul RSI with R9. And then jump loop 0. Okay. And here we should probably jump to loop 1. So here we're doing the max divide loop. It's going do the division, take the remainder to test. If the remainder wasn't a clean divide, then we're done. Otherwise, add in another power to our sum. This should always happen at least once, in which case we'll be adding in 1. And then multiply p power so that the next time through, oh, that should be R8 times RCX. Okay, so multiply R8 by RCX, then go back and go again. So then we do another divide. If that's a clean divide, we'll do this again, but otherwise we are done. I'm debating rearranging this a little bit. It's a little bit silly. So we know this is always going to succeed. So there's not really any point in doing it this way. We could do it once that here, set up p power and p sum to immediately be p and 1. Right? Then what we do is we have another divide immediately, and this is the one we actually have to test because we don't know if this one will succeed. And then instead of making this p, I can make this be a 1, so I set them both to 1. And what I'll do is I only multiply here before that, so that's always valuable work. They're both 1s. Do an extra divide here. We test it. If it's still a good divide, we increase the power and add it, and go again. Divide 2. So we don't have to. These both get to be constants that way. That seems probably like it's good. Even better if I could make these short instructions by doing that, but I don't know if that's a benefit or a drawback, so I'll kind of be inconsistent about it for now. Our accumulator gets multiplied, that part. I think we just are done. See if this is building. Okay, well, let's test out the divisor sum function. So we're gonna need a fact table. Factorial table, factorization table. So let's see, factorization table, we're going to be dealing with n's that go all the way up to 10,000. So let's just grab like a factorization table for 100, or let's not overdo it, like 20,000 slots, right? I mean, that's still overdoing it. Why don't we just do 10,000 at once? I like don't have to think about off by ones, but everything else is definitely good enough. Okay. Now, I have a factorization table, so I want to call divisor count, divisor sum. Do we have a good divisor sum function here? So we give it a fact table count and an n. Let's write an n that goes from n equals 1 to 120. That seems like a nice, highly divisible number. And we can print div sum of n, that's u64, equals LLU. Is that good? Boom. Ah, not good. Okay, so let's start by double checking. We did. Push reg. Good catch. Eighth Mage pointed out the issue, I think, which is that when this divide is not a clean divide, we're still counting on there to be a good value of n sitting in this register, but that's just not something we can count on. So RAX contains n, and then we're dividing down, 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 but then at some point we get a bad divide, and we need some way to recover the good version of the register. So I mean, I guess what we got to do is like good n equals n. Just save it, and then put the good n back in memory. Let's see if that is any better. Yeah, still crashing. That's probably a bug we had anyway. Let's just run it over here because I don't see anything wrong with the stack stuff, which is why we usually crash. So let's try debugging it. Divisor sum. Yeah, I could use a mul there, but I have a free register, so I figure why not. I mean, I'm pretty sure R10 was free, right? Yeah, I wasn't using R10. Yep, so I don't see why not. Just use a register for it. A mob is a great deal simpler than a mul. Okay, so unwinding is still working. And like, we do in fact have a factorization table here, right? I'm low on water. Okay, so after I did that, it stopped being correct. Like it stopped being good. So that's kind of strange. Let's think about that. Here we extended RSP. Here, RSP 32 would be this return pointer. It's plus 40, plus 8 from that, plus 8. That should have been reserved space for us. Two doesn't need to be in the factorization table. Our function get prime factor handles the even numbers as a separate path. So that's good. That's bad. Why is that a problem? I don't really understand. I would have thought what? So right here, I don't actually have any unwind. It's kind of weird. Take a look and see if there's anything weird going on over here. Here I've got it all. Let's, can I view the disassembly window? Looks like there's probably space here. For my function call. We fill in the parameters. Don't really understand why that's busted, but let me look at something else for a second. I want to see the U64 slots that start at RSP. Show me like 10 of these slots. So the very first one should be the instruction pointer. If I can't copy that, huh? If I put that there, do hexadecimal display, those aren't oh, of course those aren't a match. It's supposed to be, that's the return instruction pointer. So that'll be something from this line here. Is there any way I can, I don't, okay. Don't care about that. Hit that. I'm about to make this call. That's not what I said. Okay, I want to step by disassembly. Will you let me do a disassembly step? Is that? do it this way? Okay. Tuesday evening, sometimes I use the Microsoft compiler, sometimes I use the Clang compiler. I try to sort of keep both working. Right now I'm using the Microsoft compiler just because I had some kind of issue come up when I was switched to Clang with it reporting like it was reporting warnings about the contents of the PDB files or something from the Windows files I have. Like it was like some garbage I didn't want to deal with, so I haven't gone and got that fixed as of the beginning of these streams in the beginning of March, but usually I keep them both working and I'll go get that fixed soon. Okay, so our next instruction pointer, okay, let me look at the current rip. So when I do that plus 4, now I'm going to step into the current function call, but I lost track of, okay. Step by instruction a couple times. So this right here is a number I don't want to lose track of. Am I going to be able to copy that and paste it here? Okay, so that is what that looks like. Step in now, and the top of the stack looks like that. I got it off somehow. Why are we playing this music? This isn't what I put on. I gotta tell it to loop this playlist. Okay. Really confused here why I'm not getting the stack when I think I should be. I'm kind of just going down a dumb little rabbit hole here. We could probably ignore it, but there's like something weird going on where we're getting crashes that I don't totally understand. So I can't get Remedy very easily to show me. Show address. Where is the address? That's not the address. What is going on here? Okay, I was scrolled to the left, I guess. Show address, show code bytes. All right. So that's that. Rip plus 5, because I didn't see. Okay, so I didn't see all of those. I thought it was 4 bytes. It's 5 bytes. Now it makes sense. So that's fine. That is not busted. Into here we go. That's a match. 1, 2, 3, 4. These are all supposed to be free for me, right? Oh, I see the issue. Got it. So I'm doing this math as if I have pushed 4 slots, but I've actually pushed 5 slots because of this thing here. So yeah, I just need to use another slot in. I need to like consider that when I do the math. Okay. Okay, so we're not crashing, we appear to be infinite looping instead. Let's check that one out. Show me how the loops go. So our initial setup here was n equals 1, so we immediately put 1 into that. RSP, subtract 32, pop, return. So our sum, so that part is fine. The sum was good. So let's look at the next one. RDX, move n, so n is 2, we move that into here, we divide n, which is in RCX by P, which is in REX, so we're just going to get a 1 with no remainder, put a 1 there and a 1 there, we do there's the good version. We divide again. And this time we get a remainder of 1, so we jump to done. 10 has the 1 in it, so that goes back to there. Okay, so here's the issue. R8. Okay, I said I wanted to optimize that anyways, and it looks like optimizing it will also fix an issue. So here, I want to be able to count on R8, already containing n. Here, I am recovering the value of n. Right, I'm recovering the value of n. From R10 and putting it in the stack, but I'm never putting it onto R8. But I guess I do need it on the stack still here, because I could lose it after this. Yeah, but if we're already having this be correct here, we might as well say cover and stack There we go. So why does 2 say 1? 2 should say 3, right? 1 plus 2. So let's go see here. Looks like we got some kind of issue in here still. Don't care about this case. Here we go. Here's the 2 case. We don't need to look at the stack anymore. So what happens? Our accumulator has a 1. P sum is 1. So we've divided by 2 once. Ah, so this is wrong. I'm calculating that part wrong. I need to go think about that more carefully. I was a little sloppy. So after 1 divides successfully, we know that a 1 here is incorrect. We're trying to calculate the sum of the powers 1 of p to the n, where n goes up to the maximum number of divides. So we already know there's a 1 plus p in here. And if we divide again, we'll want to put a p squared in there. So we want this to start off as p. We want this to start off as p plus 1. So we could do 1 plus RCX in that case. So 1 plus 2, 1 plus 3, 1 plus 2 plus 4, 1 plus 5, 1 plus 2 plus 3 plus 6, 1 plus 7, 1 plus 2 plus 4 plus 8, 1 plus 3 plus 9, eighth mage, yeah, exactly. LEA, so that I can do it in 1 instruction instead of 2. Plus 2 plus 5 plus 10. Yeah, okay. These are looking pretty good. Okay, so if those are our divisor sums, then all it takes to compute the proper divisor sum is to subtract n afterwards, right? So we talked about before. So we're pretty much good to go here. We can... Yeah, I think the fast thing to do now is just going to be, let's use our new divisor sum function and iterate all these slots and see what happens. Let's see. Do I want to bother doing the final solution in assembly? I kind of feel like I've gotten tired of doing the uninteresting parts in assembly. So I don't think I'll bother. What I'm going to do is just solve it right here. So we're going to look at n from 1 to 10,000. We're going to grab the divisor sum. Proper sum is just sum minus n. And then we're going to get b sum is what we get when we take the proper sum right there, and we do the or b proper sum is the b sum minus the proper sum. So we do n. I'm gonna actually rename this to like m. So m sum. And here's m's proper sum, right? There's the divisor sum of m. Then we subtract m out, we get the proper divisor sum of m. And then if that is equal to n, I also want if m does not equal n here, then we accumulate n. Eighth mage, I guess I don't know Euler's formula. Let me look that up so I can tell you if it was what we did. Euler's It's not this one. Euler's. Get out of here. Example one. Solids. It's none of these Euler's formulas. I don't think so. Okay, so that's our first guess at an answer. See what happens. I'm signed out again. How did I get signed out twice tonight? All right, just... Okay, hopefully that doesn't happen anymore. All right, we were doing problem number 21, amicable numbers. Here's our solution. Right? Nope, that's not it. Okay. So what we're going to do is, instead of just accumulating these things, I'm going to have it print out all the pairs real quick so that we can kind of get an idea of what might be going wrong here. So we want to look at N and M. Where's the U32? N, oh, N is a U32. Whatever. Yep, you're right. Okay, let's start at 2. Maybe that was just it. The bug was that we were counting one as amicable, even though that's kind of like a coincidence of the formula, the way we interpreted it. Because the rest of this does look like what we would expect. Let's try that. Hey, we got one. So I think the rest of these, maybe this one we could do. Yeah, we'll read this one next. This one looks like it's on the same topic. I'm gonna take a quick walk-away break to fill up my water. Alrighty. Okay, let's take a look at the next problem. A perfect number is a number for which the sum of its proper divisors is exactly equal to the number. For example, the sum of the proper divisors of 28 would be 1 plus 2 plus 4 plus 7 plus 14, which equals 28, which means that 28 is a perfect number. A number n is called deficient if the sum of its proper divisors is less than n, and it is called abundant if the sum exceeds n. As 12 is the smallest abundant number, with 1 plus 2 plus 3 plus 4 plus 6 equals 16, the smallest number that can be written as the sum of two abundant numbers is 24. By mathematical analysis, it can be shown that all integers greater than 28,123 can be written as the sum of two abundant numbers. However, this upper limit cannot be reduced any further by analysis, even though it is known that the greatest number that cannot be expressed as the sum of two abundant numbers is less than this limit. It's an interesting comment. I don't exactly know what it means, what mathematical analysis means, but anyway. Find the sum of all the positive integers which cannot be written as the sum of two abundant numbers. Okay. So we could generate the list of abundant numbers that are less than this number here pretty easily, right? We just wrote a tool that could tell us whether a number is abundant very quickly when we did the divisor sum thing. So we run the divisor sum, and then we compare it against our input n, and that'll tell us if the divisor sum, so the divisor sum would include n itself, so then we could just subtract n like we were doing in the previous problem and then compare them. If it's abundant, we will know because the sum, even after we subtract n, will be greater than n itself. So then we get a list of abundant numbers. Then what we can do is generate this list that's the sum of all the pairs of those numbers. It's kind of a big list, but we could do it. Actually, we know, okay, so we make a table that has this many bytes in it. We clear it all to 0, and then we iterate all the pairs and mark them all as 1 when the sum is inside this table. How about that? Still an n squared iteration of the list of abundant numbers. Is there anything better we could do? It says here by mathematical analysis, we won't be able to show anything better, or it isn't known how to show anything better. So maybe it's not worth trying to be clever with this problem. And instead it's worth it to put more effort on the computational work side. But I want to just think if there's an algorithm that can help us out with the pairs of sums, the sums of pairs of these numbers thing. Testing if a number is abundant isn't the hard part. It's already done. Yeah, that's what I was saying, 8th mage. I could just do a table of bytes with this many slots in it, but I still have to do the n squared iteration of the pairs in the list of abundant numbers. And then just take a moment to think through if I could do better than that. Yeah, I mean, I could have done any of these problems by brute force. The part of the fun is thinking if there's something better to do. It kind of sounds like, according to the wording of this problem, that there isn't going to be something better to do. I think that's what this whole thing is about, which is making me think not even to bother going to the whiteboard and just typing in the solutions we score points on the website for the stuff we've already solved. It doesn't seem like there's probably two abundant numbers. Plus, we're not just discovering one number of this type, we're discovering all of them. So it's not like going backwards and doing something clever that way could help. Binary search the list to do what? One thing I guess I want to think about is, are these all going to be unique? So are there going to be a lot of duplicates where you are doing this n squared, but there's a lot of times you're hitting a sum you've already hit a different way? Or are a lot of them going to be like, this was the only way to get there? Let me think about that for a minute. So like we know 12 is the smallest one. So when it's abundant, what that's going to mean is that n itself is smaller than these things. So whenever that happens, I had it just a minute ago. Let's look at this. So before we do any thinking about it, let's just look at some data real quick. Can I look at the proper sums of some of these numbers real quick? So 12 was abundant, 18 was abundant, 20 was abundant. 24 was abundant. So there's a gap of 4 there. There's a gap of 2 there and a gap of 6 there. So I haven't found one yet that tells me this one. So that's a gap of 6. So 30 and 12 or 18, wait, 30 and 12 or subtract 6 from this one, add 6 to that one. you would get the same result from those two sums. So yeah, there's going to be plenty of duplicates. The way you would tell that there's a duplicate is that when you add those two numbers together, there's like this pattern of am I 6 away from another? Yeah, it's really irregularly shaped. I think this feels like the kind of thing where, yeah. All right, I'm not gonna do any more thinking. We're gonna just we're gonna solve this one by brute force. I'm pretty sure that that's what this is meaning to encourage you to do. It's saying there's not a lot you can do by mathematical work to simplify this problem, because we already said this is the like, here's the best thing we can do with sort of like a better understanding using some kind of mathematical grip on the problem. We get this limit. And what they're trying to tell you is like, there's not really a great clean limit, like clean way to grip the problem if you're considering numbers less than this, and we're actually asking you to consider those numbers. So probably if there is something, it's like extremely advanced anyways. Like it feels like it's getting into like, you know, the really high level number theory stuff, but more likely than that, it's probably just not even something someone knows how to do yet. So I'm not going to figure it out right now. So we're going to take that number there, and we're going to say, let's build a factor table with, nope, copy that number, that many slots in it. Let's grab right here. This is going to be our abundance. We're just going to grab enough memory for that. Abundant count equals 0. I'm going to start from 2. I'm going to grab the proper sum, and if the proper sum is greater than the sum, then abundance putter equals abundance putter. We'll write the n, and then we'll increment that guy. So anytime we find an abundant number, we'll put it there. Then we're going to grab sum table. We're going to push an array and have it clear to 0 of booleans that has that many slots. And then we're going to iterate. Let's see. Putter A is going to be starting at abundance and going to abundance putter. Putter B is going to start at abundance and stay less than putter A. And then we're just going to accumulate that into one table at the end here. 1 less than 28123. If there's not a Boolean in the sum table, accumulate that I value, and then at the end we can print out that guy right there. think we did that. No. So let's double check some stuff here. First of all, what do these look like? 12, 13, 14, 15, 17, 18, 19, 20, 21, 22, 23, 24 is on the list. Okay, so what do these look like? Wait, what? Let's get rid of that. I'm not getting any? That can't be right. No, not proper sum is greater than sum. That's a mistake. Proper sum is greater than n. So I should get 12, 18, 20. Yeah, there we go. Those are the numbers we were expecting. So that was the bug. And then let me see. If I look at this, the first number that doesn't show up should be 24. 14, 15, 16, 17. So there is one thing I might have been able to do that's smarter, is this is like very close to a triangle number, right? I'm adding up everything from 1 to this number. Okay, let's optimize this a little bit, because we have built so many cool tools in assembly. And now we're just writing C++ code because I'm feeling like I don't like writing the part of the problem that's just solving the problem. I like writing the deeper stuff in the assembly. That's the part I'm really in it for. So since I'm not doing the assembly part, let's at least practice some optimization of algorithm stuff here. So I think what we could do so instead of doing this loop here where I sum all these, what I'm thinking is I take the triangle number of that, and basically I'm subtracting the ones that we can do sums for. Of course, this isn't really any different yet, but it's a good step in the right direction. So there's that version of the answer. And then, wait a minute, I should be able to write okay, so that's a mistake. I want to include this number. It's kind of weird that these are all even. Okay, I think I just saw an odd number. It passed by kind of quick. There we go. There would have to be an odd number eventually, or else you would never be able to get to a point where all of the numbers are being hit. Of course, on this side, it looks like a lot of numbers are getting hit, but it's not quite 6, 8, 9, 5, 6. Yeah, it's like, is it better to do the ones that are included or the ones that are excluded? I don't know. But I think I can do it in one pass if I do it this way. So let me keep going. First of all, I want to go less than or equal to this amount from now on. Here I'm doing the wrong thing. I should go all the way to 21, 24 here. Or rather, less than or equal to this amount. Okay. So that's more accurate. So all numbers greater than that we know we can ignore. because those are all written as the sum of two abundant numbers. These are written as sums of two abundant numbers as well. But we aren't told that we have a clean limit on that part. So that's why we're brute forcing those. Two, three, four, five, six, seven, eight, nine, 0, 1, 2. Yeah, but by the end, it's definitely the case that lots of these are not, they're just contiguous numbers that aren't included. So then what I want to do is I want to say of abundant pair equals 0. So accumulate sum of abundant pair. We'll do it like that. Accumulated sum of abundance. So I come through all these pairs, and then I'm going to say check the table first instead of just write to it. Check the table. If there's nothing in the table, then we'll mark the table and we'll add in that sum. So every time we look at a pair, if it's the first time we've seen that number, so it's the first time we've seen one of these, we will add it to that there, and then instead of doing another loop, we can just subtract the sum of abundant numbers. And that doesn't seem like it worked out very well. It looks like we got rollover. All right, I'm gonna just take a look in the debugger at this point. Figure out what we're doing wrong here. Don't need this, okay. Ah, that's a mistake, okay. So I'm not, this wouldn't explain everything, but I need to include when pointer B equals pointer A. It's not actually going to fix anything, but it's a bug. I mean, it's not going to fix the main issue here, but it is a bug. Okay, so the first sum should be 24. Still not 24. Oh, okay. So that's going to have to start like that now. Okay, now the first sum should be 24. There we go. So we mark that and we put a 24 in there. Then we get 30, 36, 32. Yeah. Okay, so here, the accumulated sum of abundant numbers looks like that. Let me break that out into 2 lines real quick. '21, '23. Oh, this includes, no, this approach doesn't work. Unless I add in an extra safety test here, sum has to be less than or equal to 28,123, which is the limit we're actually considering. There we go. So like the issue here was I was adding things into the sum because it was overflowing the table here because I was looking at pairs of abundant numbers that added up to things that went well over the limit we're trying to use here. So then when I put the triangle number in, I got a smaller number here than I did for all the pairs I found went way over that. So there we go. Alrighty, let's see if we can get one more tonight. Okay. This is an interesting problem. So I'm going to read this one and we can discuss it. Reciprocal cycles. A unit fraction contains 1 in the numerator. The decimal representation of the unit fractions with denominators 2 to 10 are given. So that's these guys here, right? So like 1/2 is 0.5, 1/3 is 0.3 with these parentheses. And then they explain the parentheses means repeating. So like where 0.1 parentheses 6 means 0.1666 ... and a 1-digit recurring cycle. It can be seen that 1/7, this one right here, has a 6-digit recurring cycle. So there are 6 digits that are recurring there. Find the value of d less than 1000 for which the unit fraction 1/d contains the longest recurring cycle in its decimal fraction part. So we're looking to find a way to measure the length of the recurring cycle of the decimal representation for unit fractions. Okay, problem number 26. Let's explore this concept. Problem number 26. So, let's see, how do I want to start this? So, let's just write down the first few fractions here. 1/2 equals 0.5. 1/3 equals 0.3 repeating. 1/4 equals 0.25. 1/5 equals 0.2, right? Yeah. 1/6 equals 0.16 repeating. 142,857. Repeating. 1/9 equals 0.1. Repeating. Right. That makes more sense. It's gonna be like, that's not right. Okay. So what we can then do is be like, what's the score for each of these numbers here, right? So these things that don't have any repeating will get a score of 0, because that way they can't possibly be the max. The thing with the maximum repeating part. You could also see them as having a repeating 0 there, and in that way we're like, so if you have 3 digits or 6 digits repeating, that's like this much information. 1 digit repeating is like this, so there's sort of like, you're getting closer and closer to 0, whereas 0 is not like a valid, 0 is not actually a digit, right? Does that make sense? 0 is special. 0, when we write 0 by itself, it's the only 1-digit number. It's the only case where we have a like a number whose number of digits is wrong. It should be considered a 0-digit number. I don't know. I'll just leave you to think about that for yourself, because I don't feel like explaining it any more than that. But there we go. So we want to be able to figure out what's the score of one of these things. So there's some stuff that I know about things like this. So let's talk about why 1/3 is 0.3 repeating and why 1/9 is 0.1 repeating first. So, oops, sorry. If we write down let's think about what 0.3 repeating actually means. That is a sum that goes from I equals 1 to infinity of 3 times -10 to the power of I, right? So no wait, sorry, that's not right. 1/10 to the power of I, right? So the first one, the power of 1, we get 1/10. 3 times 1/10, we get a 0.3. And then, another way we could write this, like the in between these two things, is this is like 0.3 plus 0.03 plus 0.003 plus ... right? It's another way we could write it. So then the question is, why is that equal to 1/3? So what we'll do is we'll start with that sum formula. So I equals 1 to infinity of 3 times 1/10 to the I. That is, well, let's pull the 3 out, right? So it's 3 times this stuff. I equals 1 to infinity of 1 over 10 to the power of I. Okay, so this is the part that's interesting. That thing right there so if we were to sort of do it out by hand, we know that that's supposed to be 1/9, right? But how can we see that that's 1/9? If we can show that that's 1/9, we'll have convinced ourselves of two useful things at the same time. Well, we're just going to start rather than trying to derive it, because I don't necessarily know off the top of my head a clean way of showing a way to derive that. As I think about it, I'm like, not obvious. But we can definitely just prove it, right? So claim. Okay, so how do we prove something like that? How do we prove something about an infinite sum like this? Well, debating which way to take it. Do I want to look at this as a limit of finite sums and show that by epsilon delta is going to approach a 1/9? And that's the way I'm most comfortable doing it. Let's dig in. Let's see what happens. So, suppose you give me some n, or wait, epsilon, suppose you give me some epsilon, so that's a 3, not an epsilon. Suppose epsilon is greater than 0. Actually, I'll write is a real number, since we don't usually deal with real numbers in these streams, and greater than 0. Then, so our goal is to find some n so that when you sum this many things, the distance between that sum and 1 over 9 is less than epsilon. But we don't, it could be any epsilon. We don't have any information about what epsilon is, so we have to do it for arbitrary epsilon, right? We have to play this game with like a little handicap, which is we don't know which epsilon we're actually talking about. So let's look at, real quick, the pattern. I'm gonna look at like 0 is right here, 1 is right here, and there's like 9 subdivisions. So let's see, here's a third, here's a sixth, and then subdivisions into ninths. So that should be 1/9 right there, right? So there's a third, 2/3, and 1. So there's our 1/9. And we have like a 10th, which is like this thing here. And then we're adding in 1, so this guy here is 1/10. And then we add in 100th, so it's like this guy right here is 1/100th, and so on. So what's the differences here? So these are all a little bit too small. So 1/9 minus 1/10, well, that's going to be 10 minus 9/90ths. Is that right? 10 there, 9 there, yeah. So we get 1/90th. Okay, what is going to be if we do 1/9 minus 1/10 plus 1/100th? First we need to combine those guys. So 1/9 minus 11/100ths. That's going to be 100 minus 99/900ths, or 1/900th. Okay, so it kind of looks like what we can count on is whatever power we pick. Like if I pick a power of 1, then I'll get 1/90th as my delta, right? If I pick 2 as my power, then I'll get 1/900th as my delta, and so on and so on. So I want to pick an n. Let's see. If my epsilon is so let's write this out. Delta is equal to 1/9 times 1/10 to the power k, right? So if I want to create a situation where the delta is less than some arbitrary epsilon, then what I'm going to do is say 1/9 times 1/10 to the k has to be less than epsilon. And then I can solve for k here. 1/10 to the k is going to be less than 9 epsilon. Now I'm going to rearrange that to say 10 to the negative k is less than 9 epsilon. Then I can take a log and then finally k has to be greater than the negative of the log of 9 epsilon. So what we can do is say, suppose epsilon is some real number greater than 0. Then let n be equal to or let's say this, let n be some natural number where n is greater than the negative log of 9 epsilon. Then, we put in a second suppose, n is greater than our n here. Then, the sum from I equals 1 to n of 1/10 to the I yes, what we were doing is taking that amount minus 1/9 absolute value is equal to 1/9 times 1/10 to the n. So we're skipping a step in our proof here because what we should really be doing is going back and saying we observed this pattern here, but we didn't prove it. But I'm satisfied to say that we kind of like are convinced that that's just going to keep on repeating, right? Because the next thing, what's going to happen, you're going to get 111 over 1,000, and then that 111 there is going to become 999 when we cross multiply right by 1,000 there. You're going to get a 1 again, so you're going to keep seeing this difference look like that. And then finally, we can say some stuff that we know about this number here. So we know that 1/9 times 1/10 to the n, well, that is strictly greater, because n is greater than capital N, that is strictly greater than 1/9 times 1/10 to the negative log 9 epsilon. Sorry. Since 10 is 1/10 is a fraction, it's less. As the power gets bigger, this term, or this factor, gets smaller, right? Okay, and then the negative there turns this into a 1/9 10 to the log 9 epsilon. All this stuff we set up kind of just cancels each other out. 1/9 9 epsilon equals epsilon. So we get on the left-hand side this thing here, which is the difference between our sum and our target. So that difference is less than the epsilon. Okay. So what we have then is for all n, where n is greater than our capital N, we know that the sum is minus our 1/9 is less than epsilon. And then for all epsilon, follow these rules, we have, that thing again. Therefore, we can say that the limit as n goes to infinity of this thing here which is, again, that's the same thing as the infinity part. So that's sort of like a sketch of what it looks like, right? We could have finished this off by coming up with a way to prove this part. It's probably the actually interesting work had to happen there, but you get the rough idea. We can see that it's pretty clear this guy here is a convergent sum that sums to this. Now what we want to do is generalize that same picture. So once we know that, we know that this thing here is 1/3, because this is 3 times this, and that is known to be 1/9. So 3 times 1/9 is 1/3. So this whole thing then turns out to be 1/3. Right, like that. Okay, so now what we want to do is generalize this idea a little bit. So we looked at 1/10 adding up, but we need to figure out stuff like this repeating. So let's keep looking at it the other, the reverse direction for just a little bit more and look at another example. Let's just pick some random repeating decimal. I'm going to pick 1, 2 repeating. And what we need is a formula that tells us how to interpret that. So that is the same as 0.12 plus 0.0012 plus 0.000012 ... which, written as a infinite sum, looks like this. 12, 1/100 to the I, which is 12 times I equals 1 to infinity of 1/100 to the I. Okay? So we kind of see that the same thing that happened with the 3 is now happening here with the 12. We pull this part out, and what we're left with is some power of 10 being iterated like this. But this is going to turn out a little different, right? It's not going to be the same thing as 1/10 plus 1/100 plus 1/1000, because we don't include 1/10, we don't include 1/1000. We only include 100, 10,000, 1,000,000, 100 million, and so on, right? So we're skipping every other one. So that sum is going to be different. So what we want is a general formula for this part here. And then I'm going to do just another quick sanity check. But if we were to do 1 divided by 99, that's what I thought. Okay. So what we're looking at is here, this is 12 times 1/99. So how can we see that this here becomes this here? Well, I'm going to just make another version of the claim we did earlier, but this time I'm going to generalize it. So 1/10 to some random n to the I is going to be equal to 1/10 to the n minus 1. Right, so when n was 1, this was a 9. When n is 2, we get 100 here, and we get 99 here, and so on and so on and so on. Okay? Now, if you don't mind, I'll skip the proof of that, because I just did one of them, and it's going to have basically the same structure as this one, only we're going to have to deal with the fact that we were taking 10 to the n here and 10 to the n minus 1 here, and figure out some way to turn that into a closed form thing over here without the sum notation, and then come up with a plan for what value to pick for our capital N so that our limit shows, but it's going to work out. So let's skip the extra Blackboard work here. Okay. And let's get on to figuring out how we're going to use this information. So this is corresponding to a 2-digit repeating pattern, right? So the power we pick here corresponds to the number of repeating digits. So that's like our score thing. All we need to figure out now is how, when we look at 1/7, how do we go from 1/7 to, let's see, 142,857. So that's like our repeating digit number, and 1/10⁶ as the, infinite sum part. Let me actually write this a different way. How do we find that pair, right? This being the most important part, the score, and this being the digits. How do we do that? So what we need to know is what is special about, so 10⁶ corresponds to 1,2,4,8,5,7 times 1/999,999, right? If we could see the relationship between 1/7 and this, then we would be somewhere. Okay. Of course, if we were to write that out a little bit differently, we would see that we're saying 1/7 equals 1,2,4,8,5,7 over 999,999. So this is just an unreduced fraction representation for this. So something interesting about that is it means that this guy here must be a multiple of 7, right? When we reduce a fraction, we take out some of the factors from the numerator and denominator that are in common. We're taking out all of them. So what's left over are the things that made the difference. So if we took this number here, 1,2,4,8,5,7, and multiplied by 7, we should find 999,999, right? Let's double check that. Oops, I multiplied by the wrong number. It's possible I wrote it down 142. 124. Yeah, I wrote down the wrong number. It's supposed to be 142. One, four, two, 142, 142. Okay. 142,857 times 9 times 7. There we go. That confirms it. Okay. So then what's interesting about that is why don't we look at the other cases, right? So before 999,999, there's 1/9, 1/99, 1/999, 1/999, 1/9099, Okay, so these are the ones we have that didn't get used to represent 1/7. They didn't pop out of the 1/7. So now what I'm going to do is I'm going to look at the prime factorization of each of these denominators. So this is 3 squared. This is 3 squared 11. Let's see, 111. Let's pull up, is it prime? No, this isn't the one I like. Is it prime? Just give me the good one. 111, where are its factors? It's divisible by 3, so 111 divided by 3 is 37, that's prime. So we get 3 cubed and 37. Let's look at 1111. It's divisible by 11. So we get 9999 divided by 9 is that, divided by 11 is 101. Is 101 prime? It is, okay. So we get 3 squared, 11, and 101. Let's see here. So 99999 divided by 9. It's obviously going to be 5 ones. What do we get when we try to divide up 5 ones? It's divisible by 41. So let's take that divided by 41, and what's left is 271. That's clearly divisible by 3 again. Wait, no, it's not. It's prime. What am I talking about? Okay, so we pull out a 3 squared. We pull out a 41 and a 271. Okay, so admittedly that didn't show me as much as I was hoping. I was hoping I would see a pattern here that explains. I mean, clearly none of these is divisible by 7. But now that I'm thinking about it, it's like how. So let's see. 1/2. So yeah, these are the things that are 9s, and then things that are 10s. I skipped the 10s, but you can also look at all the 10 cases, right? So there's like another table over here that's like 1/10, 1 100th, 1 1,000th. 2 more to go. 1 10,000th, 1 100,000th, right? And these have 2, 5, 2 squared, 5 squared, 2 cubed, 5 cubed, 2 to the 4th, 5 to the 4th, 2 to the 5th, 5 to the 5th. So those are super simple. And anything that is like, if we have it divisible by 2 or 5, so 1/2, 1/2 uses this, 1/4 uses this. So anything where its factors are only 2 and 5, just automatically use one of these guys. So no repeating at all. They all get a score of 0. So what matters are the factors that aren't 2 and 5. And so then looking at the other numbers that we have below 10, 3 is handled by this case, 9 is handled by that case, 6 is handled by that case, because again, once you've got let's take a look here. Once you've got the ability to do, I guess, it's using, yeah, it's still using 1/9, just shifted down by 1 so that it can make, let me think about this. It makes the reduction into 6/99, which is 2/11. Let me think about this. 0.1 plus 0.06 repeating is 1/10 plus 6/99, which is 1/10 plus 2/11, which is 11 plus 20 110ths, which is 31 110ths. Am I doing something wrong here? This should probably be, no, that's right. 110 divided by 31, that can't be clean division. 1/10. Oh, that's not 6/99. No. That's just 6/90. So then we get 1/10 plus, let's see, pulling out 3, we get 2 and 30. So 1 and 15. So then I get 15 plus 10 150s, which is 25 150s. And yeah, that makes sense. So yeah, I'm not seeing how it pops out. Like I can see how if I knew the repeating cycle I was looking at, I could check a fraction, but I don't know how if I'm given a fraction, I can generate one of these things. Still unclear. So I guess I could look at this another way, which is the 1/6 problem. You start with looking at, how many of these can you get? So I guess one way I could look at this is I don't necessarily need to solve for it mathematically. I'd still like to, but let's just think about this sort of algorithmically for a moment instead. I could go look at 1/10 and compare that to 1/6. 1/10 is smaller. Try 2/10 and it's too big, right? 2/10 goes above 1/6. So this has to be a 1 because we're always looking for the biggest digit we can put here without exceeding the correct value. Then we go to the next digit and we go, okay, well, 1 would be too small, 2, we get to 1, we're looking at, 6 here, and that's not too big yet, but 7 would be too big. So you put a 6 here, and then that continues to be true forever. So you get 6s repeating. Now, how you know that you're seeing 6s repeating instead of like, oh, it's going to be 10 6s, and then on the 11th spot, it'll be a 5, and then it'll go back to 10 6s and 5, and it's 11 digits repeating. I don't know yet. And that's the thing we actually need is how many repeating slots there are. So we could figure out how to fill in the digits that way. But we can tell that 6 is going to use 1 digit by the fact that its factors are 2 and 3. So it needs to use a factor from this part and a factor from this part, right? That seems to be true. So let's look at 1/11 real quick. If I plug into my calculator 1/11, what does it look like I get? That looks like it is 0.9. Okay? And that makes sense to me because that means that it is 9/99, which obviously reduces to 1/11. And so it is selecting into this spot here. if I were to do 1 over 37, then the representation for that looks like 0 to 7 repeating. And that makes sense because that is going to be 27 over 999, which is, selecting itself into this column. And when we reduce by a multiple of 3 times, we'll find out that that's 1 over 37, right? So what about something like 1 over 13? One, two, three, four, 5, 6. So 1 over 13, sorry if that was loud. 1 over 13 looks like this. 0, 7, 6, 9, 2, 0, 7, 6, 9, 2, 3, repeating. So that means it is 7, 6, 9, 2, 3 over 999,999. Okay. Now, what's interesting about that is that suggests that 999 divided by 13 is a clean division, and it is. We also know that's a clean division of 7. So, let's look at that real quick. Score 1, score 2, score 3, score 4, score 5. Let's look at 1 over 999,999. Its factors are going to be, first of all, we know 13 and 7 are in there, so we can pull out all of that. 9 is in there, pulling out 7, pulling out 13, 12, 21. So that's another factor of 3. 407. So there's no more factors of 3 in there. $11. Okay. So this has a 3 cubed in it. It has at least one 7, at least one 11, at least one 13. And a 37. Okay. Okay, I'm starting to get some ideas about how we'll do this problem. So here we can see that any fraction we ask for, so 1 over any of these things plus any multiple of these things. If I did like 11 times 7 times 37, and just for good measure I throw in a times 4, and I did 1 divided by all of that, 8775 0, 0, 8, 7, 1, 2, 3, 4, 5. Yeah, that gives me a 6-digit repeating number. So if it's 6 digits, that means it's classing into this particular one. So my theory here, I don't know how we'll prove it exactly. My theory here is that when we look at the prime factors of these different numbers that are 1 less than powers of 10, and we try to figure out, and we look at the prime factors of our denominator d, what we're going to find is that denominator d, it has to come to a fraction that has all of those factors taken care of. So it can create the factors of 2 and 5 for free, right? So we can ignore factors of 2 and 5. But all the other factors have to be showing up here. So if I do 27, for instance, 1 over 27, it's going to have to class into score 3 because all of the smaller scores don't give it 3 factors of 3, right? So let's just try that theory. And that's a repeating 3-digit number. Now, if I did repeating by 3 and times 11, so if I did 3 times 3 times 3 to get 27 times 11 more, that gives me 297. Now, I don't think it can use this or this. Or this, because I've got an 11, but if it uses this, it won't have enough 3s. If it uses this, it won't have enough 3s. And if it uses this, it won't have the 11 it needs, right? So I think it'll have to go to 6 digits repeating. Let's check it out. 2, 3, 4, 5, 6, 1, 2, 3, 4, yeah. Okay, so that is doing 6-digit repeating. So what we have to do is take our number, throw out all the factors of 2 and 5, and then count the rest of the factors and find the smallest score that contains all of those factors. That seems to me like what's going to work. So there maybe is a different way we could go about finding this. Let me think about another way we could think about it. Maybe I'm getting too tired to actually solve this. Now that I think about it, my brain is starting to do the slowing down thing. But I'm realizing, like, okay, one thing I'd like to avoid is actually having to factorize things. We've gotten to the point where we can factorize them like implicitly. We don't actually have to build an array that tells us what the factorization is. We just use a loop, like in the previous problem, to sort of manipulate the factorization, but we don't ever actually have to build just an array that's like, here's how you factorize the number, because that is like cumbersome and slow and complicated. So, okay, a couple ideas are occurring to me here. So one thing we could do is say like, okay, if I have a number like 37 and I'm trying to figure out where to put it, instead of looking at the factorizations of all these numbers that are 1 less than a multiple of 10 or power of 10, maybe what I can do is just start writing out the decimal representation. And what I'll do is I'll go, okay, 0 is the first digit, because if I do 1/10, that's too big. So 0 is the first digit. And then it goes, okay, fine. Is 0 over 10 an exact representation of this? No. Then it goes, okay, 2. 2 is the next digit. Okay. Is 0 over 2 an exact representation of this? No. Is 0 over so 2 over 100. Is 2 over 100 an exact representation of this? No. Is 2 over 99 an exact representation of this? No. And then I guess the hard part is, like, in the case of 1 over 6, you also have to, you start having to split it. So these repeat all of their digits, but plenty of things will exist. Like, let me just throw out an example here. 1 over 15, so it's sometimes you're gonna have repeating digits show up later. So let me think of another good example of that. If I just take 11 and multiply it by 5, I bet you we'll find one. Yeah, so we get a 0 and then a 1, 8 repeating. But the 0 isn't repeating. So in order to find how many of them are repeating, we would first have to go, okay, the 0 part there is like split off, and then test that 0 over 10 plus 1/8 over 990 is an exact representation of 1 over 55. So 18 over 990 is the exact representation of 550. We could make a thing that figures out if two fractions added together are an exact representation of another fraction. That's not the hard part. But figuring out how to split the digits we've got, and also the fact that we have to generate them, it doesn't feel that much better. Yeah, I'm gonna say I think I'm too tired, because I'm not sure which direction I want to go next. There is this other idea I had just a little bit ago, which is that instead of just building like a tables for this, instead what I could do is build like some kind of jump table that would go like, okay. Yeah, now that I sit down and try to actually articulate the idea, it sounds impossible. But I'm thinking like, if I already know about where the 37s are, I could build a link from here to here that's like, you need a 37, so you start here, and then you find out you need an 11, so you jump forward. Or you start here and then you find out you need a 37, so you jump forward. But how on earth would you build something like that? That just sounds impossible. I mean, not impossible. That sounds like the wrong direction. If there's got to be a cleaner way. To answer this question, how do we go from 1/7 to the score of 6? Seven scores a 6 because it needs this many repeating 9s in the denominator. But 17 would be like the next number. So 11, 13 are handled. So yes, 1 over 17 is something huge. It doesn't even look like it's obviously repeating yet to me. So whatever it is, you'd have to keep going up until. So I guess what you could do is just iterate these things, right? And as you're going, you'd build prime factorizations for those, and you'd have to like look at all the different ways to multiply those together to build numbers. No, that doesn't seem good. I think the right way to approach it is this one, which is how do I take the number 7 and score it as a 6? Or in our other words, how do I take an arbitrary D and give it a score? So I guess there is an easy way. You don't need to know about the factorizations. You just need to know about divisibility, right? We just need to know that D divides this. So what we do is we go, okay, first of all, does our D have any factors of 2 or 5 in it? And if it does, we don't care about this number because that can't be the highest scoring number anyways, right? Like if we have a factor of 2, then we've already got somebody with the same score as this number because that was a smaller number, right? Same thing with 5s. If it's divisible by 5, then it's like maybe it's 5 times 3. Great, but we already have 1/3 in there, and it's going to get the same score as 1/3. So once we remove all of the factors of 2 and 5, we just have a smaller number that gets the same score, so we might as well ignore those numbers entirely. So we're not caring about numbers with scores of 2 or 5. We're just going to take numbers that don't have those multiples, and then we're going to score them by just iterating through these denominators here. We don't need to factorize. We just do a divisibility test, and we keep going up until we pass the divisibility test, and that gives us our score. So the repeating digit score of n is going to go like this. If 2 divides n, or 5 divides n, or let's do it this way. If 2 divides n, return repeating. Okay, let's see. If n equals, let's call this d actually for denominator. And we're going to say we assume the denominator is 1 or more. So if d equals 1, we return 0. If 2 divides our denominator, we return repeating, well, let's just write this as a non-recursive. While 2 divides d, d divided by equals 2. So we remove all the factors of 2 and 5. In our actual implementation, we won't even bother passing them into this function, but just so that the function returns the correct results, because maybe later we won't be caring so much about the maximum score, and so getting the correct score will matter. So we remove all the multiples of 2 and 5. And then what we do is we go, I guess, yeah, we actually want to do this down here, right? And then what we'll do is say, okay, if we got this far and we aren't at d equals 1 yet, then we've taken out all the 2's and 5's, and there are other factors that we need to deal with. So, we're going to do n equals 10, do a loop. We're going to let m equal n minus 1. If our d divides m, we're also going to have an s equals 1. Then return s. We have our score of s. Otherwise, we need to increment our score. We need to grow our n. And keep going, right? That's it. So there's our algorithm. I'm gonna say let's try this with U64s, and if it doesn't work, we can switch to using N, M, and D as our big numbers instead. But let's see, maybe we can do this one. Where do we want to put this? Let's try it in U64. Repeating cycle score U64X D. All right. LCM Euclidean. Hopefully this is good enough. I think if this isn't good enough, I might not bother doing it in assembly, because this would be I might just not bother doing it at all because I'm a little tired. So hopefully it works if I just keep it in U64s. I think that's all I have the brain power for right now. Okay. So what we want is, first of all, let's do divide out all factors of 2. Root 2. I'm going to move that there. Well, this one we can do in a smarter way. We don't need to use a divide instruction. Loop 2, if D and 1, go to loop 2 done. Test RCX1, jump not 0 to loop 2 done. Let's actually start with if D equals 0, go to return 0. Test RCX, jump of 0 to return 0. Return 0. Loop 2 done. Let's see. D, right shift by 1, divide by equals 2. Shift right RCX by 1. Okay. We could probably do this even better with a bit scan. Maybe that's something to play with some other day. We could just go, all right, we know it's not 0. Bit scan this from the right hand side, give us an amount, and then shift all of that out at once. Wouldn't have to be a loop. Divide out all factors of 5. So here's loop 5. This one, we're going to move RCX into RCX into RAX, and we're going to clear out RDX so that we're set up to use the divide. Then we're going to move RAX back into RCX so that if the divide doesn't work cleanly, that we have the final value back in RCX. We're going to do divide by 5. if remainder is not equal 0, go to loop 5 done. Okay, so we've removed all the multiples of 2, we've removed all the multiples of 5. We know we're not looking at a 0. So if d equals 1, and we go to return 0. Okay. So all we have left now is this loop here, which should tell us the score, right? So we need to set s equal to 1. We need to set n equal to 10. There's loop 9. Then what we do is we go m equals n minus 1. That's actually going to go into Rx because that's the numerator for our divide. So R9 dec m. Let's also make sure that our RDX got cleared to 0. We're going to be looking at dirty divides mostly, so we'll clear every time. M divide, let's see, m divided by d. D is an RCX. If the remainder equals 0, go to loop 9 done. Loop 9 done means we set the return value equal to our score, R8. But if we're not done, then what we want to do is increment our score and multiply our number. So this can work until the score gets to about 18. So what I'm going to do is throw in an extra thing here that's like, if the score gets to 17, then like panic out and let me know that it's not going to work. I have a suspicion that it's not going to work, because looking at just like the things we were looking at over here, it didn't have to get very high. I mean, it was already getting a score of 6 at 7, but then like at 17, it looked like it needed an even bigger score, and it doesn't. It skips a lot of primes here, right? So 17, 19. We could like test this out. So 1, 2, 3, 4, 5, 6, 7. 7 nines. It's divisible by 3, obviously. So let's turn that into 1, 2, 3, 4, 5, 6, 7. 239. That's a prime that was missing. What if we take that 239 out? 1, 2, 3, 4, 5, 6, 7 divided by 239. 4, 6, 4, 9. So that's primes, right? So we just got like two gigantic primes there. What about if we look at 4 ones? 1, 2, 3, 4, 5, 6, 7, 8. It's divisible by 11. 1, 0, 1, 0. Well, that's not surprising at all. 1, 0, 1, 0. I guess you get 11 anytime there's an even number of ones, huh? 1, 0, 1, 0. 1, 0, 1, 0, 1. It's divisible by 73. 13837. Divisible by 101. 137. I think that's going to be prime. Yep. So, yeah, it's like, when does 19 finally show up? That's what I'm wondering. 6, 7, 8, 9. Which I guess the easy way to figure that out is probably to run the code we've got and see if it can tell us. It's also divisible by 3. By 37. Jeez, it's so big. Yeah, I think there's not a lot of chance that that this works. It just doesn't seem like in the first 18 steps you get very much help. Okay, so let's do multiply R9 by 10. Actually, let's do, so here's what I'm gonna do. If S is greater than or equal to 18, assert. So let's see, we haven't done this yet. Compare R8 to 18. Jump if above or equal. Let's do a jump if below normal. Fair enough. Let's do mov 5 into that and divide like that. It doesn't like my int 3, so let me just try this. Okay. I'll run it in the debugger since I expect a crash. More likely than not. Let's see. First of all, we know this will work for like these numbers, so let's just try them. Score, call this D, dec repeating cycle score of D, print F, score D, equals score. All right, score of 0, 1, 0, 1, 6, 0, 1. Okay. Now what happens if I let it go to 20? Yeah. So when D is 19, it can't find a solution using 64-bit integers. So if we wanted to beat this, we would probably need to be able to do we could use our big num, but we would have to do a subtract by 1, which I don't think we've implemented. If we could do a subtract by 1, we could also do a times 10 and plus 9. That we could do. So what I'm currently doing is times 10 minus 1 times 10 minus 1. So doing times 10 plus 9 would not actually be worse. In fact, for the purposes of big num, it'd be better because then you are only strictly modifying in place. You don't need to like copy or restore a value. So we won't need to subtract. We won't need to divide by a big number. We'll just be taking the big 999 thing and dividing by our number. Let's try it. So I'm going to write it in C++ instead of in assembly because I'm kind of feeling too tired to do it that way. At least for now. So I'm going to take this out. I'm going to take out, let's see, dec, repeating cycle score. We'll put it here. Let's grab like 60 slots maybe. So initially it'll be a 9. And we'll do, let's see, U64 by N. I won't need these, I just need, I don't have an add small for this either. Oh, that sucks. Well, we will have to deal with that soon. Again, a loop. The way the loop works is, how was it? So we have M, we do a divisibility test. Remainder equals div small in place, buff D. Ah, that does destroy the buff. So we need like 2 buffs. Oops, did I just... Euler CP, thank you. Yeah, this is why I wanted to not do it in assembly first, because I'm not even sure what exactly it was that I was going to need. I sort of wanted to sketch it out at the higher level, because it's getting more complicated than stuff we've done a lot of. And I'm tired. So here I'm going to mem copy into buff 2 from buff 1. If remainder equals 0, result equals score, break, score equals 1. Otherwise, score plus equals 1. Buff 2, buff 2, buff 2. Then copy buff 2 back into buff 1. And we want to mul small in place. U64 by N, buff 1, multiply by 10. Then we're going to want to add small in place, so add 9. So there's our times 10 and our plus 9. And now we need to go implement add small in place to make this work. So there is some assembly work to do still. I don't get it. Why is that showing up? But okay, glad I caught that. Mul small in place. Yes, so we want something kind of like that. I guess I don't need to copy all this. Add small in place. U64 by N. End P. Add small U64 by 3, please. Alrighty. So, how does the add small algorithm work? Add small is first you clear out a register for grabbing the carry bit. Okay, hold on. I gotta be careful here. That's not quite right. Because here things are different. RCX. Add small. So with add small, the first thing we do in this case is we use the add that. So we're going to do clear out the R9s now. Move into RAX, the thing we get out of RCX plus 8, first slot. That's a square bracket 0, 2 now. And then we get add RAX to, let's see, RDX. We're done with RDX now. And set C R9B. So we found out the carry bit, we found out the sum. Now A0 equals R0. There we go. Then the loop begins. So putter equals the address of A1. One past last equals the address of A at size. So that's going to be R10, RDX can be our putter, R8 will be our one pass last actually. So this is going to be 8 plus RCX plus size is in R11 times 8 more. Now what we do is we start testing the carry bit. If C, the carry bit, equals 0, go to loop 0, done. Okay. if you're done, can live right about here. Now, we want to add the carry bit in at putter. Okay, so we're gonna clear out our 10, that'll be our new carry bit carrier. We're going to move into RAX from our putter, which is RDX now. We're going to add into RAX from our carry bit, that's an R9. And then we're going to set R10 based on the carry bit. And then we're going to say, okay, let's see. We have a carry bit for next time. Okay, so we want to store out like that to the pointer, the new value at that slot. We want to increment the pointer. And then am I missing anything? Sooner or later. Ah, right, yes. C equals C prime we need to do. So we move the carry bit over here, test it again. Eventually, I guess what I could do is just say, let's R8's our one pass last, we'll just move a 0 there preemptively. And then when we're all done, if OPL now is not equal to 0, a.size equals size plus 1. So we're going to inc our size register. Who's got the size? R11 does. R11 doesn't get written over anywhere, does it? Oh, it looks like it does. That's small, not add small. Okay, so we're going to inc R11 by 1. We're going to test. We're going to move into RAX the value at the R8 pointer. We're going to test that, and we're going to conditional move if that was not 0. Back into RCX from R11. Not allowed to use a memory operand during a conditional move. That seems fair enough. Okay. Okay, so that should probably work. Let's see. Of course, it still might not, but we'll see. Crazy town. Okay, we might have an issue. Let's just nope our way out of that part and step through this in the debugger instead. What's going on here? It might be that the add has an infinite loop or something. Oh, shoot. There we go. Yeah, so 19 gets a score of 18, which is why it didn't work before. But that was not so bad. We got an answer for those. So let's just see if we can run to it. I think 1,000 was all they asked for in the problem. Yeah, let's just see if we can run to 1,000. It's taking a minute. It's taking a minute. It's taking a minute. This is probably not the most effective solution, but it seems like it shouldn't take this long. So let me see. So can I just get to 100? 20 didn't take very long, but 100 we're already seeing like an issue. So 20 worked. What about 30? 30 works. 40. 40 works. 50. 50 works. 60. 60 works. 58 digits. Wow. We had to deal with 58 digits to make 1/59. And that's just the repeating bar. I don't know if there's like more. There totally could be. 70. And infinite loop. Okay, so it's between 60 and 70. Let's try one at a time here, just sort of bisecting the range. 65, infinite loop. Okay, so 65 too high. We need to go down one. So 60, 61, 62, 63, 64, 60, 61, 62. Let's try that. Okay, 60 is too high. Whoops, I just ended all of fortcutter. That was not my intention. Euler. You're still good. So 62 is too big. What about 61? 61 works. So it's when we try to run this on the number 61 that we get an issue. So let's just double check that if we isolate that, it does show up as an issue. Yeah, that's the issue. So why doesn't that one work? Let's look in the debugger to see what might be happening. I don't want this part. Get me back out. Okay. That's not good. The size is increasing more than it should be. So that's a bug in our add small u64 by n. In place u64 by n. If one passed last, we test rex. Okay, we didn't read though. We need to read first the thing at R8, which was our one pass last pointer, right? So R8 has our one pass last pointer. We need to read that, and then, there we go. Boom. Okay. So I'm feeling confident about this now. That bug made sense because that was the size of the buffer, and so it was overflowing at that point and doing something bogus. Now we're getting look like results. So $982 looks like our top result. Oh, that's not it. All right, so what we need to do, I might not try to finish this, but we'll give it a couple more minutes here. The score of this is equal to this. Let's see if we can find $982. So 1 over 983 is saying needed 982. But as far as I can tell, there's just no obvious way I can think of to verify that. Oh wait, I took the max score. That's the mistake. So 982 isn't the right answer. 983 is the right answer. It wants the D that corresponds to the max score, and I gave it the max score. That was the mistake. Find the value of D, which contains the longest recurring cycle, whereas I gave it 982, which was the length of the longest recurring cycle. I should be giving it this. Do you know what's weird? The first time we get a longest recurring cycle, it's here. And it's a 6. And then 16, 18, 22, 28, they're always one less than the number you put in. Which means there was something else to discover here. There's something else happening that I don't know about, which is cool. Look at that. Okay, so 96. When did we beat 96? We beat it at 108, which happens at 109, 112 at 113, 130 at 131, 148 at 149. Yeah, it's absolutely the case that the ones that set the new records are always one greater than the record they set. Wow. $229, $233. My goodness. That's a cool pattern. What is that? 971, 953, 937, 941. Oh, man. 887. $863. Fascinating. All right, let's try putting in 993. 983, is that right? 983, 982. Yeah, 983. There we go. All right, I think that's where I want to wrap it up. We ended up solving, let's see here, if we were to slot those in there, so there's 22 problems. We got 22 problems done, which is pretty cool. Yeah, this was a really fun project. I'm going to obviously need to practice more assembly stuff. I didn't do a whole lot of careful optimization things. Like, it occurs to me even just writing this that maybe this whole thing I'm doing with the carry bit isn't the smart way to do carry bits. So there's stuff to practice there. Never did anything with floating point numbers or SIMD. Obviously more stuff to practice there. I never did any timing on any of this, so I don't actually know. Like, it might be like things like what were we doing today earlier? The divisor sum thing. I was like playing around with using the stack like this, and that might be dumb. I would need to think about it and test it and stuff like that to learn more, but it's like, maybe there's no reason to be restoring from the stack here. Maybe it makes more sense to use non-volatile registers whenever you can. I have to think about it and study it some more. So there's stuff like that to learn about optimizing still. Um, you know, it's just a good start, but there's still a lot I need to figure out. There's also like, we ended up implementing this in C++ at the end because I was getting tired. This could have been done in C, um, or in assembly, but the main reason I didn't do it in assembly is because I was just not didn't have the brain power to do it. But separately, even if I did, there's like when we do this divide by two thing, I could be using special operands or special commit instructions that I haven't been practicing, like bit scans and stuff. Uh, so there's all sorts of stuff here that I've left to learn about. But I don't know. I feel like I have a much more solid foundation than I did when I started. So this has been cool. Yeah, I'm gonna wrap it up here. Thanks everyone for coming and checking these things out. See you guys around. Bye bye.